So Victor, from what we've learned already, we can do a nice analysis of black holes. First, let's look at an asteroid impact. Suppose an asteroid is traveling at 5.67 times 10. Oh, I like example 1. I like example 1. Example 1 is a nice question. At 5.67 times 10 to the 4th meters per second, at a distance of 1.2 times 10 to the 7th meters from the center of the Earth. How much kinetic energy would it have if it impacted the Earth? William, any suggestions of how I might want to solve this? Yeah, there's a change in height, there's a change in speed. Not with work, because the question doesn't ask how much work. So conservation of energy. William, are we cosmic? Are we in outer space? Are we doing things on a big scale? Then are any of these zero? When would potential energy be zero? Pardon me? Where is gravitational potential energy zero on the cosmic scale? All the way out at infinity. Are we out at infinity anywhere here? Now, I could have said at a distance of a very, very long ways away from the Earth. Pause for a second. To make this a little bit easier, Nina, I would say, suppose an asteroid is traveling that fast, a very long distance away, and then you could at least cross out potential energy initial. But I ask you again, are any of them zero? No. When would kinetic energy be zero if we were at rest? We started out with an initial speed. Again, if I wanted to make this question a little easier, I could say it starts at rest somehow. And it's not going to end up at rest. It's going to hit the ground with an impact. So sadly, none of these are zero. And this wants me to find, I think, William, KE final. So KE initial plus PE initial minus PE final. That's going to be KE final. You were here, weren't you?
I don't think so.
Or were you away?
Yeah, I was away.
Oh, you were away. I'm sorry. You were late twice in a row. Speaking of late, oh, no. A half m v initial squared plus Colby. Can I use this one? MGH initial? No. We're cosmic. So this is going to be a lot of typing. Negative big G, big M, little m over R initial minus negative big G, big M, little m over R final. That's going to be KE final. Does the little m cancel? There is a little m hidden in here, but I didn't say find the final speed. I said find the final kinetic energy. So unfortunately here, I don't think a little m is going to cancel. I've got to keep everything. So it's going to be 0.5. I've scrolled down. What was little m? 45,000. Not that little. V initial was 5.67 times 10 to the 4th. Squared minus 6.67 times 10 to the negative 11. Big M, 5.98 times 10 to the 24th. Little m, 45,000. All over. Our initial, I think, is 1.2 times 10 to the 7th. Is that a radius or is that an altitude? Do I need to add the radius of the Earth to that distance, or did they give it to me measured already as a radius? Oh, okay, that's the least convenient. And I'm running out of room here, so I'm going to have to use some digital ink magic and give myself as much room as possible. Then I have a minus minus, which is a, and I'm going to go ditto mark times ditto mark times ditto mark, all divided by 6.38 times 10 to the 6th. That equals, and I'm still running out of room, KE final. Pause the video for a second. I'm going to do each one of these to about 5 or 6 sig figs, I think, individually. There's no way I'm going to try typing this in one fell swoop. Way too much room for a typo. A half M V squared. 7.2335 is a good place to round off, times 10 to the 13th. 7.2335. There we go. 7.2335 times 10 to the 13th. Is that correct on that first number? People nodding. And then I have a minus 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 45,000. Making, oh, I missed a 1, Mr. Dueck. Divided by 1.2 times 10 to the 7th. Squared? Nope. That looks good. I get a negative. I didn't bother typing the negative. 1.49575. Oh, heck, 1.4957 times 10 to the 12th. And then I have a plus, all the same numbers, 6.38 times 10 to the 6th, 2.8133 times 10 to the 12th. That equals the kinetic energy final, I hope. Holler at me if any of these numbers look completely wrong, but I think it's going to be then that plus 7.2335 times 10 to the 13th, take away 1.4957 times 10 to the 12th. Let's double check for typos. I think that looks good. I'll pause here. I ended up with 7.3653 times 10 to the 13th. Did anybody else get that? Michael, yeah? Dylan? Okay. 7.3653. So the kinetic energy final equals 7.3653 times 10 to the 13th. That's how much energy it has when it impacts the Earth. Is that a lot? Well, I tried to put it into perspective for you. The atom bomb that exploded over Hiroshima had around 6.3 times 10 to the 13th joules. So this would be the equivalent of a small atom bomb. It'd do some damage. How fast would it be traveling at impact? And probably that's the question I might ask you on a test. Instead of asking you the kinetic energy, I might just say how fast. If you do how fast, you could put in on this line right here a half mv final squared, and then your little m's would cancel and it would save you some typing, but I still wouldn't try getting the v by itself. I would move everything over, I would get a number, and then solve for v. So I'm going to go 7.36. 7.3653 times 10 to the 13th. That equals a half mv final squared. Thomas, how would I get the VF by itself?
Multiply by 2.
And then divide by, and?
Square root.
Yep. So times by 2. Was M 45,000? No, yes? Yep. And square root of that. Yeah, it's moving when it hits the Earth. And this might be maybe kind of what made the dinosaurs extinct, although I don't know how big the mass of that asteroid was theoretically. but it would have been hauling pretty fast. 5.72 times 10 to the fourth meters per second. And I think I already showed you the Neil deGrasse Tyson asteroid video, yes? Example 2. Another nice application of stellar dynamics. Geosynchronous satellites maintain their orbit over the same place at all times, somewhere over the equator. What would the period of a geosynchronous satellite be? You should know this and be able to figure it out in your head. If it's staying above the same place on the Earth at all times, how long must it take for it to go around its circle? 24 hours. How many seconds is that? Do the math, Dylan, on your calculator. I know I said see formula sheet, but you're going to notice, and I think I may have mentioned this before, there's a bit of a discrepancy here. If you go 24 times 60 times 60, is it 86,400? That's how long 24 hours are. So that should be the period of the Earth, shouldn't it? But if you look at your formula sheet, it doesn't say 86,400. What does it say? 86,100. Why? Have I done this little song and dance before? I did. It's the difference between how long it takes the Earth to spin around once on its axis and how long it takes the Earth to spin around and see the sun again coming over the horizon. Remember that the Earth isn't at rest. It's also moving around the sun. And so for it to see the sun again, it has to perform slightly less than 360 degrees of rotation. I usually use this one, but I'll let you use either. I'm not that fussy. And if you're lazy like Dylan and you just want to use the one from the sheet, go ahead. What's the radius of such a satellite? I guess they would all have to be at the same radius and same speed because they all have the same period. Are they in orbit? Gravity is what's pulling me in a circle. Good yawn, Maddie? Yeah, now I get your name right. Big G, big M, little m over r squared equals m. Which acceleration equation am I going to use here for moving in a circle? Oh, because I know the period. 4 pi squared r over t squared. A little m cancels. Does an r cancel? Is this the one we're going to have to use a cube root? The fact that Mr. Dueck gets such a delightful giggle out of that because we get to use a mathematical operation that you thought was useless, does that mean there's a higher likelihood than average that this might be the type of question that you might see in the future? I don't know. I'll let you ponder the wisdom of that statement yourself. So I think I'm going to get r cubed. You know what? I'm going to cross multiply this way. Big G, big M, t squared over 4 pi squared. That equals r cubed, cube root. I think. So r is going to be the cube root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. I'm going to use 86,400 squared. Dylan, if you want to use the 86,100, seriously, and we'll see how our difference, how close we are, okay? All over 4 pi squared. .67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 86,400 squared divided by bracket 4 pi squared, close bracket, cube root. Oh, wrong button. Somebody at the door there, or did someone just?
No, it was in there.
Okay. Let's try that again. Cube root, which is button number 4, answer button. I got 4.23 times 10 to the 1, 2, 3, 4, 5, 6, 7. What did you get?
4.21.
So you're good to 2 sig figs, and that's what I usually mark these two. I'll take either. Okay. But yeah, first of all, pretty high. All of our GPS satellites, I believe, are geosynchronous, and many of our communication satellites are. It's very handy to have a satellite that stays above the same area at all times. Now let's get into some black hole dynamics. Turn the page when you're done. I like example 3. I like example 3. Example 3 is a nice question. Suppose an 18,000 kilogram spaceship is orbiting a black hole at an orbital radius of 8.8 times 10 to the 9th meters. The black hole has a mass of 6.8 times 10 to the 32 kilograms. What was the mass of the sun? 10 to the what? I don't care about the front part, just the 10 to the 30, 10 to the 32. So this is about roughly 100 times heavier than the sun, give or take. Okay. What's the gravitational field strength at this radius? I will be asking you a gravitational field strength question. I didn't give you the gravitational field strength formula on your sheet. Or did I? On your sheet, I gave you this. Right? Basically, what I'm saying is, if you take the gravitational universal gravitation equation and you divide it by little m, then the little m would cancel, and that's really your gravitational field strength equation hidden in the combination of the gravitational force equation and that. After that, Victor, it's plug and chug. Complicated plug and chug, but plug and chug. The gravitational field strength at this location from this black hole would be 6.67 times 10 to the negative 11. Careful, don't use 5.98 times 10 to the 24th as a habit. We've got a new big M. 6.8 times 10 to the 32. And our R squared is 8.8 times 10 to the 9th squared. Oh, that's a typo, Mr. Dueck. Y'all get 586? And you could call this meters per second squared, but since it's a gravitational field, I think newtons per kilogram. Would this be fatal to those on board the spaceship? Why or why not? Why not? No need to do any math. What's the gravitational field strength on the International Space Station? It's about, what, 9.1-ish? Do the astronauts notice it? Why not? They're in free fall and they're in orbit. As long as they are in free fall orbit, they won't notice it. Now, getting into that orbit or leaving that orbit, then it would become problematic. But at least here, you'd be okay, I think. The only issues might be a gravitational field strength that strong might actually pull on the bottom of the spacecraft slightly stronger than on the top of the spacecraft, just in that distance. And so there might be some weirdness going on there. I'd have to run some numbers. So we're around a black hole, so we're pretty theoretical here anyways. We okay with that? We're having some fun. What's the escape velocity required to leave a black hole? To leave, and here's how I phrased it, the black hole's gravity well. How did we find escape velocity? There will be an escape velocity question on your test. How did we find escape velocity? It should be called escape speed. What approach did we use? How much work? This question didn't say how much work. What did we use to derive our equation for escape velocity? We didn't know. We're not in orbit, so we can't. I'm glad you said that. Colby asked, did we use FC equals FG? If we're trying to leave, are we in orbit? No, so we can't say that. Good. So we can eliminate one. If we're trying to leave, are we going to want to change in height? Conservation. But it was a strange one. I'm going to start it up here because we need some room. I'll change colors. It was a strange one, Thomas, because we started out with our old familiar friend. Starting to see why I do the echo thing for conservation. It really is a universal law, and it's very, very handy. But here's what we said. We want to end up at the edge of the universe. So what's our final potential energy? Yeah. And we want to do it so perfectly that right when we get to the edge of the universe, we coast to a stop. So what's our final kinetic energy? And so we had this strange expression where we had a half m v initial squared plus negative big G big M little m over r initial equals 0. Although then it ended up being a really nice clean equation, because then, Thomas, we said, well, we got a negative term. Why don't we plus it over to the other side? We also noticed that the little m would cancel. You could cancel on this line. I think I usually canceled on the next line. But if there's a 0, you can also divide the 0 by m, and we're okay with that. And we ended up with a half v initial squared equals positive big G, big M over R initial. And then we found, V escape was 2 times big G times big M over R initial square root. It wasn't twice the size of orbital speed. It was root 2 the size of orbital speed. Well, kind of cool. I'm totally running out of room here, so I'm going to have to go to my calculator, but I'm also going to cheat just a little bit. I'm going to bring back this, which has almost all the information. I have to stick a 2 times, and I have to get rid of the squared, and then it's going to be the square root of this, I think. Probably should be significantly larger than Earth's escape velocity, which was 11,1111. Yep. Oh, yeah. Doable. We're not the speed of light. I'm going to go 3.21 times 10 to the 1, 2, 3, 4, 5, 6. Is that right, folks? Yeah. But you know what? We're in a sci-fi world. Maybe this spaceship can go that fast. Okay. Let's suppose just before we fire our engines, someone decides that their dream has always been to know what's on the other side, what's inside a black hole. And so they get into a little tiny escape probe, and they launch their escape probe into the black hole. What would it be like to fall into a black hole? I've had to change my answer as of a couple of years ago. Put your pencils down, look up. A black hole has a mass of 7.2 times 10 to the 31 kilograms. Suppose a spaceship is that far from the center of the black hole. What's the gravitational field strength at this location? Let's see. We said if you take the force of gravity and you can't, just divide by m. This was our gravitational field strength equation, kind of hidden on your formula sheet. Okay. It's going to be 6.67 times 10 to the negative 11. 7.2 times 10 to the 31. This black hole is only about 10 times, roughly, the mass of the sun, roughly. So I'm guessing it's probably going to be a bit of a smaller answer. And don't forget the squared. $6.67 times 10 to the negative 11. 7.2 times 10 to the 31 divided by 9.6 times 10 to the 9th, times 10 to the 9th squared. Is that right, Mr. Dueck? Looks good. 52.1. Anybody else? Yeah. Newtons per kilogram or meters per second squared. What's the escape velocity required to leave the black hole at this location? How do we find escape velocity? Conservation of energy, but both of your finals are 0. Okay. We just derived that equation, so I'm going to, because you're kind of getting tired, it looks like, just reuse it. It was 2 big G, big M over R squared? No, just R. So it's going to be the square root of 2, 6.67 times 10 to the negative 11. Big M was 7.2 times 10 to the 31. And R was 9.6 times 10 to the 9th. I can almost reuse these numbers if I just backspace and edit. If I insert a 2 times, and then I just delete the squared, square root of that, and I get 1.00 times 10 to the 6th, almost exactly 1,000,000 meters per second. That's a fluke, but we'll take it. I like C, I like C, I like C. C is a nice question. So at what radius from the center of the black hole does the event horizon begin? Where is the point of no return for light itself? What we're going to use is we're going to use the escape velocity equation. And we're just going to let v equal the speed of light, which I think was 3 times 10 to the 8th. But we're going to get the r by itself first. Where is the r right now? Inside the... So first thing I'm going to do, Thomas, is I'm going to square both sides. You actually look at, I think, square root equations in Math 11. I think, holy smokes, this is also useful. We're gonna get v squared equals 2 big G big M over r. And now to get the r by itself, to find out what radius the event horizon starts at, it's going to be 2 big G big M over v squared, where v is going to be the speed of light. So I'll replace it with the letter C just to be fussy. You don't have to, but I will because I'm a nerd. It's going to be 2 times 6.67 times 10 to the negative 11 What was the mass of this black hole? 7.2 times 10 to the 31. And the speed, 3 times 10 to the 8th squared. I can bring some of this back. Oh, this is nice. Yeah, 2 times that times that. I just need to divide this by 3.0 times 10 to the 8th squared. So if this star can't collapse smaller than that radius, this star can never form a black hole. We need the gravitational pull of the mass of this star to be strong enough to collapse it in on itself, dense enough so that its radius gets less than 106,720. 1.07 times 10 to the 6th. Basically, I think the radius of the Earth was in the 10 to the 6th range, yes? This massive star would have to collapse smaller than the radius of the Earth. Otherwise, it wouldn't form a black hole. It would form some other stellar object, a white dwarf, a red dwarf. There's other things that it can... It all depends on how much mass there is and how dense you can get it. Well, you know I have a fondness for destroying our solar system and our universe. So, example 5. Suppose the sun began to collapse. Johnny, question? Just go too fast?
Yeah, that's right.
You can copy it out if you want.
Yeah.
You got it all? You sure? Okay. Suppose our sun began to collapse, maintaining its mass, but its radius continually decreased. At what radius will it become a black hole? Now, that radius is called the event horizon. When you're forming a black hole, it's also called the Schwarzschild radius. And you can then, there's other conditions to tell you whether or not it's feasible for that particular mass of star to become a black hole or not. So we want to find R. We said, again, we use the escape velocity. V escape equals the square root of 2 big G, big M over R. I think we went like this. We went like this. We got V squared equals 2 big G, big M over R. We got R equals 2 big G, big M over V squared. And again, we're going to let V equal the speed of light. So I'm going to be fussy. I'm going to put the letter C there because that's what we're talking about. 2, 6.67 times 10 to the negative 11. Mass of the sun is what? 1.98? Is that right?
Yeah.
Times 10 to the 30th, is that right? Wow, I dredged that up from nowhere. 3 times 10 to the 8th squared. What's the sun's Schwarzschild radius? How small must it collapse? You know what? I can just modify this equation by replacing this with 1.9 insert 8 times 10 to the 30th. Haha. Look at that, Mr. Dueck. You get 2,934.8. And that just gives you an idea of how dense we're talking about black holes matter becoming. Ridiculously, my brain can't wrap my mind around it at all dense. So 2,900. You know what? Since that worked out so nicely, I'll do the whole thing. All the mass of the sun would have to be compressed into an area smaller than, into a volume, into a radius smaller than that. Otherwise, it can't form a black hole. What's your homework? Your homework is any homework you're missing and the ultimate review. On Wednesday, I'm going to give you a take-home quiz. We'll mark it next class, and I'll talk